Hello, grade 12s. Mrs. Dunphy here, ready for lesson 4.1. I miss you guys. I hope you're all doing well. Hopefully we can get through this together, and let me know if you have any questions. So I've included on your LMS site, there's class discussions. There's a place that you can access all the course notes, and then whatever I save on my smart notebook, I will save that as a PDF so you can use that. And then once a week, we're going to hand in questions. So because it's Easter, you can hand it in Monday. And there's a problem set area there where you can upload with that scanning tool to save it as a PDF. And if you have any questions, let me know. So this is new for me. We're going to try to get the lesson on to Zoom here. So we're starting a new unit. So we finished up with our statistics unit, and now remember I said it's kind of the big umbrella of counting and probability. So this unit is about permutations, combinations, and Pascal's triangle. So this week we're going to cover organized counting, permutations, and then we're going to have a recap day. So how every week is going to look. So we have 4 weeks until the beginning of May. We're going to cover 3 topics or 3 sections a week. And those questions are, there's some there you can just do practice questions, and then there's questions that you have to hand in. Okay, so I'm going to have a lesson for today, 4.1. I'm going to have a lesson for tomorrow, 4.2. And then on Wednesday, I made a handout for practice. I know some of you don't have a printer, so I made everything a PDF, so hopefully you can look at it on your smartphone. And please let me know if you have questions, because this is a tricky topic. I know that we've done statistics, but now that we're moving into counting, things start to get tricky. So, combinatorics. So it's a branch of mathematics dealing with ideas and methods for counting when you can't just count simply on your hand for large number of possible arrangements or outcomes. Okay? So when you have to make a series of choices, you can determine the total number of possibilities without actually counting each one individually. So remember I was talking about the license plate. That's going to be one of our questions. So how many license plates are there? So we're going to be learning the first type of counting method is called a tree diagram. So I'm just going to highlight. Tree diagram is one of those first counting techniques of how to count. We can use a tree diagram to help us. So here I have Grace, lives in Hamilton. She's planning a trip to Rome. She checks a website offering inexpensive airfare, finds if she travels through London. So first she's going to go to London. So there are 3 flights available from Toronto to London. So that's like the first leg of the trip. There's 2 flights from London to Rome. That's the second leg of the trip. Sorry, the first leg here is taking the bus, plane, or train from Hamilton to Toronto. So how many ways can she travel from Hamilton all the way to Rome using tree diagrams to set this up? Okay, so I'm going to actually teach you. So I have this little pen thing here. Let's see if this works. No. Okay, so method, yes, method number 1. Sorry if it's a bit messy here. So method number 1 is going to be the tree diagram, and then I'm going to show you a different way that you can solve this. Okay, so tree diagram. So basically when you're dealing with a tree diagram, you want to think about the different stages. Like think of the different stages of her trip. So she started off, like where did she actually start? Yes, if you said Hamilton, you are right. So she started off in Hamilton and she had 3 choices. She could have taken a bus. Oh goodness. Hold on. Let's just undo that. So she could have taken a bus, a plane, or a train. So this is kind of like my first leg, if you will. So this is leg number 1, where I'm going from Hamilton to Toronto. And then leg number 2 is now I'm here in Toronto. So to go from Toronto to London, so that's leg number 2, I can actually go on 3 flights. So essentially I could take a bus, flight 1, a bus, flight 2. So from each of these options, I can branch out 3 times. So that's why they call it a tree diagram, because it branches out. And you do kind of get a little messy here because there's so many different ways. And I'm going to tell you, tree diagram is not my favorite way to count because it does get long and messy here. And then the last stage, so this is from Toronto to London. And then the last stage is from London to Rome. So I had 3 flights coming out of each one. So I could have taken train, flight 1, bus, flight 1. Now here I am in London. So for me to get to London to Rome, then I need to branch out 2 times outside of each of these. So even if I did, let's say plane, flight 1, so all of these have branching out. And I'm just going to kind of draw 2 just to speed things up here, okay? So if you count how many branches are at the end, right? You've got 2, 4, 6, 8, 10, 12, 14, 16. I missed something here. 2, 4, 6, 8, 10, 12, 14, 16, 18. Thank you, Ms. Dunphy. There you go. 18 ways. Okay, so there's 18 ways she can travel from Hamilton to Rome. Then the next method is what we call the slot method. And this is the method that we're going to be using for the rest of the unit, whenever order matters. I'm going to talk more about order mattering tomorrow when we talk about permutations. So the second method is what we call the slot method. And it's kind of a funny name, the slot method. And it means you have to think about different stages. So each stage is like a slot machine. So slot method. Okay, if I tried, I think I'm learning that if I write too fast, that's when things happen here. So slot, there we go. Method, perfect, okay. So what is the first slot? So how many choices do I have to go from Hamilton to Toronto? How many choices do I have for the first slot? Well, I could have done a bus, a plane, or a train. So I had 3 choices. I'm going to use a dot for multiplications so we don't confuse it with X's. Okay, stage 2. Next, I go from Toronto to London. I could have taken flight 1, 2, or 3. Then the last stage is London to Rome. I could have taken those 2 flights. And if we multiply them, 3 times 3 times 2, we actually also get 18 ways. So clearly we like the slot method better. It's way less drawing, that's for sure. So when you're asked to do a tree diagram, so I think one problem, I have you guys do one tree diagram. So when you think about tree diagrams, and in your homework as well, think about how many choices. So there's like a sandwich question in your homework about, it's like talking about mustard and roast beef. So number one, of course. So construct a tree diagram to illustrate the possible contents of a sandwich made from white or brown bread, ham, chicken, or beef, mustard, or mayonnaise. So the first stage is your type of bread. So you've got white, brown. Then from there, you're going to choose your meat, ham, chicken, beef. Then from there, mustard, mayonnaise. So think about each stage, like each leg of the trick, okay? All right, so next example, here we go. This is definitely not the same as being in class, but hopefully this is making sense. And please send me any class discussion questions you want to go over from the homework. I can take them up on Zoom. I can take them up when we do our office hour Thursday, or I can also take up the question and just post it. Okay, so remember I talked about the slot method. That's actually a fancy word. So this is the slot method. Okay, it's called the fundamental, multiplicative counting principle. So whenever I think of this, I think of the word and. So she went to Toronto and London and Rome. So and, okay. So and, when I think of this, I think of and. And we had to multiply each stage. So the fundamental multiplicative principle means you're multiplying. So when a task or a process is made up of stages, whether it's digits, whether it's windows opening and closing, that's another one, I think. So anything that has different separate stages. So the window opening and closing, that's number 12. A large room has a bank of 5 windows. Each window is a stage. Is this window open, close? 2 choices. This window open, close? 2 choices. So every time you have separate stages, the total number of choices can be found by multiplying. So we're multiplying stage. How many choices in the first stage? N, the number of choices for the first stage. N, the number of choices of the second stage. P, the number of choices of the third, and so on. Okay, so the idea is and means multiply. And then in the next example, or means add. So this or that we add, this and that we multiply. Okay, so let's think about how many stages when we're talking about license plate. And I think you have a homework question about zip codes. So it's the same idea. So in Ontario, our license plate consists of 4 letters followed by 3 numbers. So let me think about this for a second. If I'm determining the number of license plates that can be issued, what is an example of one? Like, am I allowed to have A? Okay, all right. I see what you're doing here. Just, oh, I can make it thinner. Oh, no, it's fine. Oh, goodness. Sorry, guys. So yeah, can I make it like this? Could I have duplicates or 4 letters in a row? Oh, sorry, my favorite number is 3. Could I have 0, 0, 0, right? I could have any number of digits. So I could have just done 0, 0, 0. I could do any number of ways. So let's just say, I don't know. Let's go back to 3. So the idea is each one of these digits or letters is a stage. So that's just me kind of thinking off to the side. So now I want to actually complete the problem. So how many different ways can I have a license plate? I guess I'm going to be doing, there we go. So in Ontario, you can have 4 letters followed by 3 numbers. So each, this is why I call it the slot method, because I make slots. Okay, so I have slot, 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 and every single slot multiplies. So hopefully I didn't confuse you. I shouldn't have separated them so much there. So let's put them together. Okay, so we have 7 slots. How many choices do we have for the first stage? If you can have any number of digits, I'm sorry, letters. If you said 26, good job. There are 26 letters in the alphabet. And there's a homework question that talks about, actually, I don't know, maybe if there's capitals and lowercase, that'd be 52. So 26, but again, I could have, again, an A, an A, an A, an A, right? So I have 26 choices for each stage. It doesn't say they have to be repeated. Sorry, that was the homework question. If it says a number can't be repeated, or a letter can't be repeated, 26, 25, right? So if you can repeat it, it's going to be 26 each time for all of those slots. So my choices for each stage was the number of letters in the alphabet. Okay, so there's 26. Now, how many numbers? We have 3 numbers here. Sorry, how many choices do I have for this stage of a digit? I can have 0 to 9. So I do get 10. And you're going to notice in your homework, that's the first thing kids say is like, this is the answer in the textbook. This number's huge. Counting is big. Counting is a huge, you know, you're going to get huge numbers. And that's why a lot of combinatorics is related to computer science, because they're dealing with such large numbers. So the answer, and please always double check. I might make my mistake of the day remotely. Okay, so there's a lot of, you know, we're talking 456 million different license plates. Okay. All right. So hopefully the takeaway from this example is think about stages, whether it's a window, whether it's a digit, whether it's a type of sandwich topping. Okay, it's different stages with different choices per stage. Okay. The next example is about, so I just saw this in the homework and I wanted to put this in as an example. Just to kind of show you that like every question is different. That's what makes this unit so tricky is, you know, what slots do I make? How many stages do I have? How do I think about the question? How do I start? And that's what makes it so tricky. So I wanted to give you lots of examples. So here I have an example about the final score of a hockey game is 2-3. How many different scores were possible after the second period? So you don't really have to know how to play hockey. I've never been to a hockey game. So just so you know, there's 3 periods, but basically it's just saying at some point in the game. The final score, so let me think about this. The final score was 2-3. So the first team got 2 points, the second team got 3 points. So what are some possible scores that could have happened in the second period? This is how I start to think about stages. Could they have had no goals? Could it have been 0-0 after the first or second period? All of a sudden they score a lot. Could it have been 3-1? But the first team final score was 2-3, so that's not going to work. Could it have been 2-2? Okay. Could it have been 1-3? So this is the idea of now stages, is getting my head around what are these slots. So when you're talking about the fundamental counting principle, you're trying to think about how many different stages, how many different slots. So when it comes down to it, we actually have 2. We have the first team score. So this is the number, I guess I shouldn't say number 1 because technically they didn't win. I should say, you know, I like to kind of give my slots subscripts, right? So this slot here, I like to give them subscripts. So my slot here, I said, okay, you represent Hamilton to Toronto, you represent Toronto to London, you represent London to Rome. Here, this slot represent an alphabet number, a number. So I like to kind of give myself subscripts so I know what the slot means, and then I can determine how many choices I have for that slot. So here I have the first team possible scores. So how many possible scores could they have had? They got up to 2 points. So they could have had 0 at the second period, 1 at the second period, or 2. So we have, remember it's talking about how many choices per stage. So they have 3. Then we have team, so the second team. They could have scored 0, 1, 2, 3. So they have 4. So there's actually 12 different scores possible. And it's funny, I've had students do on quizzes and tests, literally listing all the scores or whatever the question was. Clearly you couldn't have done every single license plate, but some of the answers are pretty small, right? 12, but I can't give full marks because you're not using the fundamental counting principle, which is what is in your curriculum. So make sure you use the slot method, okay? You can always count for fun. Don't do it for big numbers, but yes, this in the homework, you technically could have just written out the scores. Okay, so hopefully that makes sense. There's a question like that in the homework. Oh, yes. So our last example is about, our second last example, I should say, is about the OR. So we're looking at the rule of sum, OR. So the additive counting principle, or the rule of sum, is we're looking at this or that. So this is the adding. So when using a counting action, that things that can't occur at the same time. So when counting things, they're called mutually exclusive, you can apply the additive counting principle. So if one mutually exclusive action can occur in m ways, a second in n ways, a third in p ways, then there are m plus n plus p ways. Which one of these actions can occur? So how many ways can you roll a sum of 5 or a sum of 10 with a pair of dice? I've had some students, believe it or not, that aren't sure what dice are. So here's my little visual. So a die is a 6-sided game tool, dice, and it has the numbers 1 to 6. So if you roll it, this has a 1. If I roll this one, ooh, that says 1. There you go. Wow, that has never happened. 2 ones in a row. My lucky day. I should go buy a lottery ticket. Oh my gosh, maybe it's stuck there. There you go. So this is a sum of 6 because 1 plus 5, right? You add them together. So 1 plus 5 is 6. So if this die can go all the way from 1 to 6, this die can go all the way from 1 to 6. The lowest sum you can get is 2. And the highest sum you can get is 12. So this little diagram explains the different sums. So a sum of 5, you can get 1 and a 4, 2 and a 3, 3 and a 2, 4 and a 1. And I like to show the visual of the 2 color of dice because students sometimes say, well, isn't 4 and 1 the same as 1 and 4? Well, no, because you can distinguish between the red and the blue die, right? 1 here and a 5 there, right? If I have a 1 and a 5, that's a different roll than this being a 5 and that being a 1. That's a totally different roll. If you remember back to that first die I got, so I had a 1 and a 1. Those are called indistinguishable. So it's like, well, is it the blue die or the red die? You don't know which one was 1 and 1. They're just 1 and 1. So there's only one way to get a double of each. So there's only one sum of 2. There's only one sum of 4. There's only one sum of, you know, the 3 and 3, 4 and 4, 5 and 5. So if a die gets a double, that's 1. But 3 and 2 for a sum of 5 is different than 2 and 3. Okay, similarly for the sum of 10, oops, same color. A sum of 10, let's just get rid of the 2 and the 12, that has 3 choices. Can you ever roll a 5 simultaneously as a 10? I mean, you know, there's no way. So these are mutually exclusive events. They can't occur at the same time. So another way I like to write it down is using coordinates. So how many ways can I roll a sum? Okay, so sum of 5 and a sum of 10. So using this little coordinate, system, if this little table, you know, there's another way you can write it down here. So a sum of 10. So this is the first die, 2, second die, 3. But having this is different. So it just kind of lets me organize my counting. 4, 1 is different than 1, 4. So there's 4 ways to count a sum of 5. Sum of 10, we could have done 6, 4, 4, 6, but the 5s, right? So we talked about they're indistinguishable, whether it's a red 5, blue 5. So you only have one option there. So there's 3, 4 ways here, and there's 3 ways here. So using the additive counting principle, how many ways can you roll a sum of 5 and a sum of 6? So therefore, 4 plus 3 is 7. Okay. So knowing when to add or when to multiply, this is a big giveaway, right? If you see or. But sometimes the word's not there, right? With the hockey game, that's why I put that one in there, because it's not the same. It doesn't say and, it doesn't say or. And same with the license plate, right? I need a letter and another letter and another letter and another letter. It's not like or, it's an and situation. So and I find is more popular than or. So or you're adding. Just to also, I've encountered students that haven't had experience with a deck of cards. I'm going to put in an example for that so that helps you for your homework. Okay, so just to review, right? We had sum of 5, pause, sum of 10, or, because it can't happen at the same time. Okay, thank you for your patience. Good job. Last example, just to kind of review a deck of cards. So I usually bring a deck of cards to my lessons at school. So a deck of cards has 52 cards in the deck. There's 4 different suits. So you have like a diamond, or sorry, a heart. So there's a heart. You have a diamond. You have a club, which is the little flower. And then you have a spade, which is black right there. So there's 2 types of reds, 2 types of blacks. There's 4 of each card. So there's 4 kings. I found 3 of them here. See if I can quickly find the 4th king. So I have 4 kings. Okay. If you ever see face cards, jack. So there's a jack, queen, king, jack, queen, and there's a kings. Okay. We start with ace. So it has a little A. So here's my ace of spades. Okay. So how many ways could you choose 2 aces, one after the other from a deck of cards? Okay. Now, remember, this unit is counting. It's not probability. So next unit, we are going to say, what is the probability you choose 2 aces, one after the other from a deck of cards, right? This is looking at, so in this unit, every single question breaks down to how many ways? How many ways could Grace travel? How many ways can you have different license plates? How many ways are there to have the scores of the hockey game? So how many ways could you choose 2 aces, one after the other? So you have to think about those slots again. So assuming you get it, right? You're not talking about probability. You're just talking about how many ways. So you're choosing two aces, one after the other. So they do depend, right? Whether I pick it second or first. So I have two stages, and it's and, because I need to get this ace, and I need to pick an ace, and pick another ace. So how many ways can I pick an ace? How many different aces are there? Well, I could pick any of the four. So there's 4 ways to pick that first ace. So if I've picked that first ace, and here it is in my hand, how many aces remain in the deck? Well, I've used an ace. So there's 1 less ace because you've picked out an ace, so it's 3. So 4 times 3 is 12 ways. So this is choosing 2 things. I'm picking an ace, then I'm picking another one. So it's dependent. Pick one, pick another. Versus how many ways could you choose a red 9 or a club? So this one was saying I need 1 ace and I need another ace. This one is saying how many ways could I choose a red 9 or? So I'm just picking 1 card. How many ways could you choose? How many ways could it be a red 9 or a club? So a red 9, so red, let's just do it in red, why not? A red means a heart or diamond. So how many red 9s are there? 2 plus a club. Okay, and I think I wrote that on your sheet. You have an updated handout there. Okay, so if you know there's 52 cards and there's 4 suits, there's 13 of each. So there are 13 clubs. So there are 15 ways you can pick a red 9 or a club. Okay, so thank you so much for your patience, and I will see you tomorrow for our next section. Okay, thank you, gals. Bye, guys. See you tomorrow.